The sky offered an interesting mystery that grew louder with each new camera frame. Scientists raced to point major telescopes in Chile, Hawaii, and space. Messages were passed between experts at Atlas, NOIRLab, STSCI, and the James Webb Space Telescope Group. Interest rose fast because the object moved on an unusual path. Spectra and images promised strong facts about an object from another dimension. This video will walk you through those facts and what those telescopes found. Stay with us. But what exactly was this strange traveler racing through the night sky? A comet, an asteroid, or something beyond our models, entirely something that might challenge everything we know? How it was found. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, known as ATLAS, reported a new moving object in the southern sky. ATLAS scans wide areas each night from Haleakala in Hawaii and flags faint moving points. Within hours, the Zwicky Transient Facility in California and Pan-STARRS in Hawaii reported matching detections. Observers noted a fuzzy glow around a bright center, a sign that gas and dust were forming a cometary coma. The Minor Planet Center received the positions and ran orbit fits to test possible paths. Observers in Chile and the United States moved quickly to confirm the discovery. Gemini South on Cerro Pacun and the Southern Astrophysical Research Telescope took deeper images that mapped the tail and tracked brightness changes. The NASA Infrared Telescope facility measured heat in the near-infrared, while many smaller observatories fed time-stamped images into public archives. Scientists searched older survey data and found the object in pre-covery frames from the Transiting Exoplanet Survey satellite and Pan-STARRS. Those older frames showed it faintly weeks earlier, which helped refine the trajectory and the timeline of activity. Researchers from Caltech, Harvard, the University of Arizona, and the University of Hawaii compared data and shared refined positions, color measurements, and early spectra. Private groups led by Matthew Hopkins, Bryce Bolin, and Darrell Seligman posted technical descriptions describing initial fits and models for gas release. Early low-resolution spectroscopy and narrowband imaging from ground-based spectrographs detected lines and features that suggested volatile release. Those early spectra indicated ongoing outgassing rather than a single explosive event, and observers watched the coma brighten for a couple of days. The Minor Planet Center and participating observatories updated orbital solutions as new positions arrived. The improved fits revealed a hyperbolic eccentricity, a key number showing the object is not bound to the Sun. Observers measured an incoming velocity higher than most solar system comets. That speed and the hyperbolic path led teams to classify the object as interstellar and to assign the label 3I Atlas with the provisional designation C2025N1 for publication and tracking. Data flowed rapidly across both public and private working groups. Staff at the Space Telescope Science Institute in Baltimore prepared target lists and requested high-resolution Hubble images to try to separate any nucleus from the surrounding coma. Within days, the Hubble Space Telescope was scheduled to observe and provide sharper views. Ground telescopes continued nightly monitoring to measure changes in tail length and direction so that scientists could estimate particle speeds and dust grain sizes. The quick global response yielded a dense set of observations from survey cameras, medium telescopes, and flagship observatories. Those combined data gave a clear record of discovery, early composition hints, dust measurements, and a precise orbit. The coordinated effort set the stage for follow-up time on the James Webb Space Telescope and other instruments to study the object in infrared detail. Observers also noted that the object is the third confirmed interstellar visitor overall. But sharp images alone weren't enough because hidden inside that glowing blur could be a clue to whether this was just cosmic debris or something far stranger. What did Hubble really see? What Hubble and ground telescopes showed? The Hubble Space Telescope returned very sharp images of 3I Atlas. The team at the Space Telescope Science Institute used those images to separate the bright coma from any solid nucleus. Their analysis set a conservative upper limit on the nucleus diameter near 5.6 kilometers while noting the solid core could be much smaller, perhaps just a few hundred meters. The bright cloud of dust and gas around the object makes direct measurement difficult. Ground telescopes added important context. The Gemini Observatory on Cerro Passion in Chile took image sequences that showed a growing tail and steady brightening over several weeks. Scientists at the National Science Foundation's National Optical Infrared Astronomy Research Laboratory processed wide-field frames to track tail length and shape from night to night. Observers at the Southern Astrophysical Research Telescope and at Cerro Tololo Inter-American Observatory ran follow-up imaging to map how dust fans changed with time. Those working in the infrared used the NASA Infrared Telescope facility to measure heat and search for icy grains. Near-infrared spectra showed a flattening at longer wavelengths that matched the presence of large water ice grains in the coma in some analyses. Spectrum shapes and color trends from Gemini South and the Infrared Telescope facility helped identify dust particle sizes and basic surface properties. Surveyors supplied early views before the official discovery. NASA's Transiting Exoplanet Survey satellite and the Vera C. Rubin Observatory recorded the object in archived frames. Those precovery images showed faint activity weeks earlier and helped refine the orbit. Comparing images from different dates let astronomers confirm that activity began far from the Sun and then increased gradually. The steady rise in brightness pointed to volatile ices driving the outgassing rather than a single outburst. Scientists measured coma brightness and converted light into dust production estimates using standard comet models. They tracked how the tail length changed and used those measures to estimate particle speeds. Smaller grains moved faster and formed a broader fan. Larger grains moved more slowly and stayed nearer the main trail. Tracking speeds over several nights let them estimate grain sizes and mass loss rates in kilograms per second. Observations from the Neil Gorell's Swift Observatory detected emission associated with water breakdown in late July and early August. Those signals suggested water vapor or sublimating ice grains were present in the coma at that time, though different teams report varying signal strength. Optical spectra from some large telescopes also showed gas features such as cyanide and faint metal lines in the coma. Taken together, the Hubble data and groundwork produced a layered view. Sharp Hubble frames provided limits on the nucleus and revealed structure in the inner coma. Wide-field and infrared data measured tail length, dust speeds, and the presence of ice grains farther out. The set of observations guided the community toward the next round of observations, and teams shared data widely online. Many university groups and students contributed observations that quickly filled gaps in the public record. But just as scientists thought they were piecing the puzzle together, a new signal changed everything. What if the real story wasn't water at all but something far stranger waiting to be uncovered? Webb's first look, the carbon dioxide signal. On August 6, 2025, the James Webb Space Telescope used its near-infrared spectrograph to observe 3I Atlas. Webb recorded infrared light from the coma and produced a spectrum that shows how different molecules absorb and emit energy. The spectrum contains clear bands that match carbon dioxide. The carbon dioxide features are stronger than the water features in the parts of the coma Webb sampled. The SPETRX mission recorded matching infrared features a few days later, giving independent confirmation. Spectroscopy works by comparing observed light to laboratory fingerprints for known molecules. Carbon dioxide has strong, well-known bands in the infrared that Webb can see clearly. Water also has bands in the near-infrared, but in these observations, water bands were weaker. Observers also found smaller amounts of carbon monoxide and faint traces of sulfur-bearing molecules such as carbonyl sulfide. Teams at Caltech, Harvard University, and the University of Arizona ran independent fits to the spectra to check results. To turn band strengths into physical numbers, researchers use laboratory cross-sections and simple coma models. Laboratory cross-sections show how strongly a molecule absorbs at a given wavelength. Using that data and the measured band brightness, scientists estimate how many molecules are present. Those numbers convert into gas production rates expressed in kilograms per second. Multiple groups ran that conversion and reported consistent ranges for carbon dioxide and lower rates for water. Webb spectra also revealed line shapes and Doppler shifts. Line widths and shifts give information about gas motion in the coma. A broader line usually means faster-moving gas. Measured gas speeds for the observed bands fit the range expected for cometary outflow at these distances from the Sun. Scientists combined gas speed and production rates to build physical models of activity. Those models test whether gas escapes from a few localized vents on the surface or from a larger area across the nucleus. Current fits narrow the plausible options, but do not yet eliminate either. The high carbon dioxide to water ratio can come from several physical causes. One possibility is the formation in a cold region of a protoplanetary disk where carbon dioxide ice condensed and remained abundant. Another possibility is a surface layer that traps water ice below while carbon dioxide escapes from shallower layers or from fractures. A third possibility is long exposure to cosmic rays and interstellar radiation that altered the outer layer and reduced surface water. Webb and SPITRX numbers help teams test these ideas by comparing measured ratios to model predictions. The James Webb Space Telescope results guided ground-based follow-up. Infrared features identified by Webb set target wavelengths for the Gemini Observatory on Cerro Passion and for instruments at the NASA Infrared Telescope facility. Observers used that guidance to plan deeper exposures and to monitor spectral changes over time. The Webb run produced a clear chemical snapshot and a baseline for later comparisons as the object moves closer to the Sun. Research groups will soon publish papers as they refine models and add observations in the coming months. But if the chemistry tells us what this visitor is made of, its path tells us something even stranger: where it truly came from. And that answer may challenge everything we thought we knew. What kind of story does an object speeding in from interstellar space really carry with it? Orbit, speed, and where it came from. Astronomers used measurements from the Asteroid Terrestrial Impact Last Alert System, the Zwicky Transient Facility, the Panoramic Survey Telescope and Rapid Response System, the Hubble Space Telescope, and many ground observatories to compute an orbit for 3I Atlas. They measured positions over several weeks and fit a path through the solar system. The best fit showed a hyperbolic orbit with an eccentricity greater than 1. That value means the object is not bound to the Sun. Astronomers calculated an incoming velocity higher than normal for solar system comets. The speed and direction place the object on a high-energy path through the inner solar system. Current orbit solutions put perihelion near October 29, 2025. Perihelion is the point at which the object comes closest to the Sun. The closest approach to Earth is later, around December 19, 2025, at about 1.8 astronomical units. 1 astronomical unit is the average distance from Earth to the Sun. Researchers used the measured path to trace a rough incoming direction through the Milky Way. Some fit points toward star fields in the constellation Sagittarius and toward the thick disk of our galaxy. Other fits shift in that direction by many degrees. Small errors in velocity or position grow into large changes when tracing a path across interstellar space. Over millions of years, gravitational encounters with passing stars and the galaxy can bend a path. Those factors make exact origin claims difficult. And don't forget to like and subscribe for more discoveries.